And don't worry, I was asked by technical team to talk a little bit longer, just to make possible for Sushi to come here. So sorry for this short technical break. And yeah, let me introduce myself. My name is Marcin, and currently I'm working at Sigmoidal as a senior deep learning engineer. And as Marek already told you, I want to tell you something, give you a short lecture about variational dropout and positive unlabeled learning. And it will be actually a short impression because actually one of the projects which we were working on made us to use this technique. It's not that we are curious from the scientific point of view how this works, but our task was so hard that we need to use a really sophisticated technique in order to achieve good results. Unfortunately, I will skip the part of how the task looked like, but I will show you the simple case study on how to use these techniques in order to improve your prediction models. So, just to start, I want to ask you guys how many of you know what dropout is, because in order to introduce variational dropout, it's good to know what dropout is. So how many of you know what dropout is? Cool. How many of you use this? Have already used this? And how many of you stopped using this? Because this is actually the case. Currently, although dropout is a really cool technique, it's believed that there are other techniques which perform the same thing what dropout is actually performing in slightly faster way. So it's like, I will mention it later, that today many new neural network architectures actually don't use dropout, which is really also really interesting. But just to introduce dropout to you, just to know what dropout is. So dropout is a regularization technique. So a technique which make your networks to overfit less, and it's doing it in a really interesting manner. So basically, when you have a neural network and you are training it, you have a lot of weights, you have a lot of units which are taking part in the prediction and backpropagation stage. So what is actually dropout doing? During the training time, dropout is with, so I will introduce you with the let's call it vanilla dropout. Each unit here are turned off with a set probability. And this probability is, let's assume that it's constant, and for each of these cases, we are simply flipping a coin, which succeeds in with a set probability. And if we choose this unit to be turned off, during the inference time, we set its value to 0, no matter what the input to this unit was. So, how this actually works? To understand why dropout is actually a really cool technique for regularization, you need to understand what usually neural nets which are overfitting doing with their input. So usually, when net is overfitting, there are parts of the network. Let's assume that this unit, which are responsible for memoizing a certain cases. Like for example, if you have 10 examples in your data set, a network like this would likely, or for example 5, just to make it easier, it's relatively, it could happen that each of these 5 units will memorize each of these inputs here, and they will simply, see at the new input. It will check if such input was memoized, and then give the prediction based on this. So memoizing is not a good thing in neural networks, because if you could memorize your inputs, maybe neural nets are not the best algorithm to use in this case. So we want our units not to memorize things. So let's assume that a first case in our data set is memorized by this unit. So with a let's say probability of a half, this unit will be turned on during the prediction. So the responsibility for predicting the good answer for this case is spread off among other units. So in this case, this unit and this unit. And this is how dropout helps us in this case. And this also showed to us yet another really interesting property of dropout, that dropout makes each of these units to learn general things, because they cannot learn specific things, because if they learn specific things, which will be then, which then prediction will be solely based on this specific unit, then with a given probability, when this unit will be turned off, then your network will suffer a lot. So dropout is actually making your network to learn general things. And it's believed, because it's hard to prove anything mathematically in the deep learning domain nowadays, that it also imposes sparsity, but because of the fact that we have 30 minutes, I will skip this part now. And as I mentioned earlier, nowadays it's believed that also a new technique of normalization, of regularization, called batch normalization, is doing similar job to dropout. So just to speed up training, relatively often batch normalization is used instead of dropout. From our experience at Sigmoido, we noticed that in case of when your data set is really small, it's good to use both of these techniques. And when your data set is relatively big, this is actually a fact that batch normalization is a sufficient regularization technique. But yet, it's worth to, in case of small data sets, it's even worth to try both of these or any combinations of these techniques. From my experience, I would also share my thought that it's really good to use dropout along with L2 regularization technique, which from my experience is really, really good. Okay, and the last thing, which would be really important in later, is that it also allows us Bayesian deep learning, which I will talk about later. Okay, but before that, just to make sure that we know how dropout works. So during the training phase, for each batch, there is this dropout mask set. The network is trained with such connections. For the next batch, we are performing yet another sampling. For example, let's assume that maybe this unit might be actually turned off, and we do this yet again. And it's really interesting because what is performed in a classical dropout during inference time? Because if you think about it closely, so first of all, in classical dropout, you don't have this masking during the inference. So think about it. Then this layer is actually usually expects that input from this layer would be lower than it will be if every unit will be turned on. When every unit will be turned on, because usually part of these units were turned off. So what is actually performed is that usually the input from here is rescaled in order to, in some way, to prevent the fact that this layer will have the input which it doesn't know. So this is also, you have many techniques on how you could rescale this input, but this operation is also actually performed during the inference time. Okay, so just to show you an example on how dropout works, I will show you a simple case study where we have a digits data set and we have to recognize 5s. So this is binary classification problem. So what we could see here, that without dropout, we can see a slight overfitting pattern where our validation loss is a little bit higher than training loss, and the same with accuracy. But what is really interesting is that the features which are learned by network during this process, as you may see, these features are pretty concrete. There are a certain pattern of 5s which are learned here. So this is, I think, the most obvious example where you have almost exactly 5 here, and these blobs here actually also they could also introduce this overfitting pattern, which I mentioned earlier. That if, for example, that this network could actually make our network to overfit more. And in case of dropout, you might see that what I've said is actually happening. So first of all, the network is unstable a little bit. It's obvious because we are sampling actually parts of the network to be cut off. But we don't have this overfitting pattern. Actually, we have underfitting pattern. But our features are much more spread, and the responsibility for making decision are spread across many units, and they are making so they have on one hand similar things to do, because other units should be prepared for example, this unit to be turned off. But on the other hand, this is spread just to make the decision better. So this is how actually this is yet another some kind of meta regularization which Dropout is performing, which is making your model more robust, and just to makes your model to know your data in much wiser way. Okay. So now let me get to variational dropout. So this term was first introduced by Gal and Garmani in 2015, and just to explain it in a really simple way, what does it mean how would you introduce variational dropout to your model? Is that you are simply not turning off dropout during also an inference phase. So basically, during an inference time, you are sampling functions by simply turning off part of the units also during an inference. And this is why it's called variational, because you are sampling functions in this way. And what is and of course, in order to make good predictions, you need to do this multiple times, because of the fact that during one inference call, you could actually turn on a unit which will actually make your inference worse. But in general, for example, in our cases, we usually mostly sample it 10 times. In general, it makes your predictions to be better. And to be honest, this idea was first introduced in an original Dropout paper, but these guys provided in their paper a really cool explanation that variational dropout could be actually interpreted as some kind of Gaussian process. And since this time, this technique is usually referred to be variational dropout. And this technique, where you simply keep the dropout turned on also during an inference, is usually referred to as Monte Carlo dropout, or Monte Carlo dropout sampling, because you are simply sampling from this variational distribution here. And what is the coolest thing about this, if you think about this carefully, is it's hard to say if this actually provides you with better results, because if it would, you would probably hear about this really, really often, because this is a relatively simple technique to make your performance of your model better. So from my experience, it's also that yes, it's usually slightly better, but in some cases it's worse. But what's the coolest thing here, and this is what Marek already mentioned, that this approach provides you with the uncertainty of a model. And how this is actually made, this is a really, really interesting thing. And to understand this, let me come back to this example. So try to think about a case when in these 10, let's assume that we have these 10 calls, that in these 10 calls, your results from your model are consistent. So what is most likely to happen is that the case which is provided during an inference is known to a model, because probably the information, the signal about what decision should be made for this model was introduced to a model during a training phase. It's really unlikely that for 10 different crops here, you will have similar results in case when the input you are providing wasn't relatively well presented in your data set. So basically, sorry? So So basically, so this uncertainty, which was mentioned here, is providing you with the information if model is sure about its prediction in these terms, that it shows you that, okay, this case was in my data set, and I know what decision should be made for this case. And later on, I will show you that this is actually happening. And of course, the biggest downside of this approach is that you call this multiple times. And in terms of implementation, it's really nice because, for example, in Keras, you could introduce variational dropout within, I think, 4 lines of code. So it's really nice and also really easy to implement. And if you are interested on how to do this, we could talk about this later. So, practical example on a really interesting practical example on how variational dropout could actually provide you with better results and also with the measure of uncertainty is something called Bayesian segnet. So, for those of you who doesn't know, segnet is an architecture which is used for image segmentation. So, given an image, you want to provide this. Let's call it class mask, where for each pixel you're assigning some class usually from the predefined set of class, which model believes that this pixel belongs to. And here you may see the original picture, here you may see the ground truth, here you may see the prediction, and the most interesting part is the uncertainty prediction here about the prediction for a given pixel. And you may see that usually when surface is changing, like for example from the asphalt to concrete, its model is not so sure about what decision should be made. And this is interesting because, as you may see, there is a line painted here, and model doesn't have a problem with this line. There is a single line here, and whereas you have 3 lines here. And the case which I really like is that, for example, here model is expecting. Model is expecting to see a person, so it's not sure if there is something. But the most funny one is that usually when you are taking such picture, there is a car mask here. So model is also looks for these car masks here. So this provides you not only with results, but also shows you some interesting insights about how. What actually is performed, so what kind of computations are performed in your model during the inference time. Okay, now I want to get to this other topic, which is positive unlabeled learning. So this is a subdomain of the positive learning which Marek mentioned earlier. So in case of positive unlabeled learning, you have the following setup, that you have a subset of positive examples, and what is worth to mention that usually this set is relatively small, and it's really expensive to extend it for further examples. You may think about, for example, medicines or genes that you should perform a really complex analysis of for a new data point. But you have this subset of positive cases, and in this case it's really hard because usually you may think, when you are thinking about this problem, there is some kind of process which is providing you with examples for which should be tested. So of course you have negative examples in this sense that during this procedure some cases are classified as not belonging to this positive class, but introducing these examples to your training phase is actually pretty risky because you have this bias that there is a pre-selection process where you choose these examples which should be tested for a given property. So this was also in our case. Just to show you, in one of our cases, we have data from our client, and we computed some statistics about this data. And this training data here so these orange blobs here are distribution of these statistics from our training data which we get from our client, and these blue ones are actually the data which come from the source of the production data, where you should actually apply your model. So as you may see, this distribution is completely different, and training your model only on these orange blobs, because there you have not only positive but you have also negative examples, could be actually could bias your model, as model completely don't know how to. So what should be? It's hard for model to decide what decision should be made for these examples, as during the training phase there wasn't so much of signal to model parameters in order what to do here. So this topic is so it's not a well-known problem. We noticed that approximately there are 3 papers about this a year. So it's like it's not a mainstream. It's rather a side case. And so the simplest techniques which are used in this case are usually based on some kind of neighborhood and distance. That you are simply computing the distance for a new example to positive examples around it. And if, for example, this distance is below a given threshold, you could classify this as new example. And you could do the same using kernel click and SVM here. And so what's the problem with this? That actually, in many cases, you cannot introduce any valuable metric which will actually measure the distance between 2 data points. As for example, it's hard to introduce metric between different statistics about genes or medicines. So this is the huge problem here. And other technique is that what Marek already told you, that you could put all production samples which you get, because usually you have a relatively easy source to get with these unlabeled data. It's hard to label them, but it's not hard to get them. And you are simply collecting such data set, and you're introducing them to your data set as negative examples, and then using probably some kind of probabilistic correction, you're trying to predict the score values for new examples. And just to mention my favorite technique, which is called the SPY technique, where from your training data, you are cutting a set of spies, and you are putting them to your unlabeled data with negative label. And then you are making decision based on this model scores on this spionage equipe, just to know how model is actually performing on positive data. And actually, this technique was also used by us in the simple case study, which I want to introduce you now. Okay, so what was our case study? So in our case study, I will show you this based on artificial case study, where once again we will use a digits data set, and we took fives, and out of 5,000 fives which you have in this data set, we took 1,000 as known positive examples, and other 4,000 we simply classified them as non-fives. Then we trained, in this case, a really simple model, which is the same network which we introduced before. And here we actually applied a really interesting treatment in terms of weighting samples and weighting classes, where we actually, based on some Bayesian assumptions, we computed what this weight should be in order to make training feasible. And it turned out that this was actually crucial, that without setting this reweighting, training is actually pretty hard. But in our case, it was we managed to do this. And we trained this model where we have only these 1,000 positive examples and 59,000 of negative examples. And once the model was trained for a new example, basically here you have 2 kinds of new examples. So first kind is cases which were non-tagged as 5 in your training set, because you cannot say if these cases are 5s or not. And other testing data is simple testing data from digit data set. So here, what was really interesting, that results on both of these data sets were almost the same in terms of almost all metrics. And here I want to show you how the model performs. And in order to make an inference on new cases, we take the mean out of 10 samples of variational dropout. So we simply run our model 10 times with different setups of dropout crop. And as uncertainty measure, we took the standard deviation of these probabilities out of these 10 samples. And so it's also good to know that this standard deviation we took in order of simplicity, because it's believed that there are other metrics of this uncertainty which are better, and usually in most of papers, this STD is not working good. So just to briefly tell you what kinds of metrics could be applied here, is that you could get because what model actually usually outputs is the probability distribution over classes. So it has some entropy. So one of the most successful measure is that you could, for each of this sample, you could compute the same. So here you have one output, which is the mean of these 10 outputs. And here you could, for each of these outputs, compute the same and take a mean of this. And as entropy is a convex function, if you compute entropy of this minus mean of these entropies, this is always a positive number. And this is something which is called bold. And this is believed to be the best. But this is simply something which I wanted to mention, that using STD in your production maybe is not the best idea. There are better metrics which could be easily found in papers. And so let's look at the results. So as you may see, there is a really nice banana shape everywhere. So just to explain you what the axis of these graphs are, this axis is the prediction in terms of probability. So this is this mean of these 10 samples, and this is this. So this should be STD actually here, and it's normalized to be in interval from 0 to 1. So for example, this example, the model believes that is non-5 and is really certain about this prediction. For example, for this example, model is relatively certain that model is relatively sure that this should be should be 5, but it's not so certain. As you may see that you have 60%, there is 60% of uncertainty here, and the same in this example. For this example's model is likely to give prediction of 1 and is relatively certain. So what is nice, that with the when model is assured in both of these with respect to both of these metrics, that both prediction is high and uncertainty is low. So this is a really promising result. And what is also really nice is that, as you may see, most of examples of 5s are here. And because of that, these 5s are these 1,000 5s which were introduced to our dataset as actual ones. Actual 5s, and these ones are 5s which were said to be non-5s. So it's really nice that this distribution, there is of course not a threshold where these 5s are well separated, but on the other hand, you may see that they are mostly concentrated here, and you still have this banana shape, which is really nice. And what is really good is that non-5s, there is actually a threshold where my model actually knows that this shouldn't be 5, which is really good. And here, I'm not sure if everyone could see this picture. So how many of you see this picture? Because we call this method a diffusion method. And to explain you why, is that during a training phase, for each example, so here red examples are training 5s, so these 5s which are correctly marked as 5s. Green ones are not 5s, and blue ones are those 5s which were said to be non-5s in our dataset. So as you may see, cases which are close to red examples, during a training phase, these cases received a signal that they should go up with their probability, because they are around other samples which model gives a signal to have probability of 1. And in every case from this sum of of blue and green set at each iteration phase, iteration of training during the training phase, gave a signal to go down with the probability. So this is why we call this diffusion, because these cases actually, these cases which were non-5s actually went down, and these cases which were 5s, they stood in with the probability which is close to 1. And this is what we expected to happen, and this is actually happened, and we are really, happy that our intuition was correct, and that's why we call this diffusion. But there is yet another thing which we introduced. There is yet another thing which we introduced, because as you may see, usually in these cases, what you are most interested in is to get new candidates for a research to test if these cases are actually positive cases. So you want your model not only to discriminate between positive samples and other samples, but also to be good at this, because you may lose a lot of money when you will check cases which are actually not worth to look at. So as you may see, if you, for example, cut these cases with respect to this uncertainty, so if you, for example, look only at this part here, so this classifier is almost perfect, because here you have a lot of 5s, and number of 5s is really low here, and it's really good here and here, whereas the number of 5s here is really low, and number of non-5s is good, really big here. So so what we do is that we cutted cases with respect to their uncertainty. So here you may see 10 different AUC curves, and each curve is for different uncertainty threshold. So if you took only cases which model is certain with the level of uncertain at the level at most of 0.1, you have AUC almost at the level of 1. And when you introduce cases which model is more uncertain, the AUC drops, and even that these values are still pretty high, you may see on the ROC curve that you are actually here, you are losing a lot of cases, whereas this might be actually pretty costly for you. So, and this also has a really funny interpretation, because as you may recall, because we have different models, so what we are doing, we are performing these, let's say, diffusion in different realities, because model is actually introducing this reality where you have the score of this model, which is in some way half of the cases, and you are simply looking at different universes, and you are checking if the results are the same across these universes in order to diffute positive samples from negative ones. So I want to also mention that it wasn't that we use this technique, just to be cool, because we always strive to provide as simple model as possible. But this case was really, really hard, to be honest with you. And we were made to use such sophisticated technique. So we are really satisfied that we succeed. And yeah, I hope that you also like this. And I'm really curious about the questions you have about what I just taught.